In this problem, we're trying to figure out the force needed to hold this length of pipe in place. The way we'd go about this, we'd first need to figure out the volumetric flow rate through the pipe. We'll need to figure out the pressure at location 3, and what we'll do is just assume major losses across it. So we'll use setup energy equation. Typically what you would do is, this is the method in which we would solve it. The way we'd work through it with students, use this equation, come up with the friction factor, come up with the volumetric flow rate, and then we'll figure out the pressure at the fitting. So it's a pretty typical fluid mechanics problem. In Engineering Equation Solver, what I've done on the right is I first established temperature and pressure that we're dealing with. There's a couple of functions in Engineering Equation Solver that will return the density and the kinematic viscosity. I put the parameters from the problem statement in here. Note that I'm using dimensions of meters afterwards in square brackets for the dimensions. Diameter of 60 millimeters. Here I'm converting millimeters to meters. We're given a relative roughness. In this problem, epsilon over d is 0.002. Set alpha to 1. Here's my area. And then here's the simplified energy equation. And then what's convenient about ease is that it will solve for the friction factor as a function of the Reynolds number and the relative roughness. And it does it iteratively. It's a numerical solver. It doesn't matter what order we put variables in. Here, for example, I've got the Reynolds number after I've used it for the first time, so it's smart enough to figure this stuff out. And then some calculations to figure out the pressure. And then at the end, if you want to report it in English units, for example, you can easily convert from newtons to pound force. So once I've got it laid out, I can use the solve button here, and it will iteratively solve the problem. And it gives me the results here. One thing I could do is, for example, if we're trying to figure out the force in pounds, we might want two significant figures. I can highlight this, a box for it, and if I figure out my force. It's also really handy that it will tell you, it will call out any issues associated with units. To set the units, I go up here to variable info, and then areas in meters squared, for example. Kinematic viscosity is meters squared per second. Some of the functions will accept pressures in kilopascal. And let's say, for example, we'll make a mistake. Let's say here the diameter, instead of meters, let's pretend that it's in millimeters. To do that, I would come, if I made a mistake and I left the diameter in millimeters instead of meters, and when I run it, it's calling out, there's a number of potential unit errors. So it's saying, we're off by a factor of, in this case, 1,000,000 if we're squaring the area. So it'll give you a heads up on all of this. So the unit handling is really convenient. It's also got some handy built-in functions. For example, we could answer a question fairly easily. What's the mass flow rate of water? If we've got a temperature and pressure specified, a length of the pipe, 10 meters, for example. Let's say there's a pressure drop of 2 psi across the pipe. We'll convert that to kilopascal. We've got the pipe diameter and relative roughness. The way we'll do this is go Options, Function Info, and we're here at Heat Transfer and Fluid Flow, Convection. And we're going to look at internal flow throughout the length of the pipe. In this function here, I'll paste this into the code. The way these functions work, there are input variables to the left of the colon and output variables to the right. So here we'll specify the fluid. Instead of air, we'll say it's water. The temperature, we'll say is the room temperature of the room, pressure of the room. And this is what we're after, is the mass flow rate. The diameter we've set, length of the pipe we've set, relative roughness. These variables, if you want them, are heat transfer coefficients. I'm going to comment them out using these curly braces because we don't need it, nor do we need the Nusselt number. So I'll comment those out. The function will return delta P, but the algorithm's smart enough to know that it needs to solve for the unknown variable, which is m dot. So all of this goes on behind the scenes, and it will return the friction factor and the relative roughness. So when I go up and run, when I solve the problem, we see a pressure drop about 13.8 kilopascal, which corresponds to 2 psi. And then what we're after in the problem is a mass flow rate. So maybe I'll highlight this with a box. Let's just report two significant figures on that. We see a mass flow rate of 7.2 kilograms per second.